Welcome to Pomodoro Joe for Sunday, May 14th, 2023. Today we're looking at LeetCode problem 1799. Maximize score after n operations. This is a hard problem. So you are given nums, an array of positive integers of size 2 times n. You must perform n operations on this array. In the ith operation, 1 indexed, you will choose two elements, x and y, receive a score of I times the GCD of x and y. Remove x and y from nums. Return the maximum score you can receive after performing n operations. The function GCD x comma y is the greatest common divisor of x and y. Okay, so we have some examples. There's nums 1 and 2. Well, the GCD of 1 and 2 is 1, so you output 1. All right, that's pretty straightforward. Next we have 3, 4, 6, 8, and we have output of 11. How does that work? So looks like we have 3 and 6 where the GCD will be 3, and 4 and 8 where the GCD will be 4. So we choose 4 first because we want that to be, we choose 3 first. We want to use the higher multiplier later. So we choose 3 first, so 3 times 1, and then 4 times 2, so that's 3 plus 8 is going to give us 11. All right, let's look at our constraints. The constraints are pretty good here. N is between 1 and 7, so we have up to 14 numbers, which makes this a very small set, which is very convenient. The numbers themselves, though, can be quite large, so we have to be careful with that. All right, with that, we'll put 25 minutes on the Pomodoro timer, and we will get started. So I think we will just follow the recipe they lay out right here. We'll choose two elements, we'll do this calculation with the I times our GCD, then we'll remove those elements from our nums, and we'll recurse. So this is a recursive solution. All right, so let's start out with an internal function, def max score recurse. Now, what will we take here? In this one, we'll be taking our remaining numbers and our remaining operations, because we need to keep track of how many operations we've performed so far. So I'll have some remaining numbers, and I don't know, I'll call it remaining ops. So that'll be just the count of how many operations we still have left. All right, so internal, we will have our base case. What's our base case here? Well, if we don't have any numbers, or if we don't have any remaining operations, then we're done, and we can return 0. So if not our remaining nums, or not remaining ops, then we're done and we return 0. All right, so that's just saying if we don't have any numbers or we don't have any operations left, we return 0. What's next? Well, according to our recipe here, we choose two elements, x and y. So for this, we'll want to choose essentially every combination of our elements left. So we'll just go through every I, j, or x, y in our remaining numbers. All right, so for every I in, let's calculate our length out here so we don't have to do it more than once. Okay, so for every index in the range of our remaining numbers, then we will grab that index, and we need to find the GCD with some other index. So then for every j in range, and this will be I plus 1, because we don't want to use the same number twice. So we have to go to the next index, I plus 1, but we still go through the length of numbers. And I was silly, I created a variable for this, so I don't need to do this. Same thing up here. All right, so this will give me my two elements that I'm going to pick out of our array, find the GCD for these elements, and then we'll add that to our current result. So let's see, we'll need some value here. So our current value will be I times, well not I, our remaining ops times. So this is going to be how many ops we have left. So this will be our, what they call I over here. This is our ith operation. So the remaining ops times our GCD of our number at I and j index. So this is going to be remaining nums Okay, so this is our remaining number of operations times the GCD of our nums at I and j. Now, this GCD, we could define it on our own. This is the greatest common divisor. There are some fairly simple algorithms for this, but since this is Python, we have libraries. So I'm just going to say from math import GCD. Now, if you're not using the latest version of Python, if you're on a Python 2, this may not be there. I have to go back and double check. If it's not there, you can still write your own GCD function. It's actually not that hard. I'll try to leave some links in the description so you can check it out. All right, so this is the value for this particular op. We're saying this I times our GCD xy, and now we need to remove x and y from our nums. So we're gonna have some new nums here. Okay, or new remaining nums. I'm just gonna call it new nums because it's kind of getting along, the name's getting a bit too long. Okay, so our new nums are just gonna be, well, so in this case, because Python passes by reference, meaning we're sharing this same remaining nums if we were to pass it on or make changes to it, I really don't want to make any changes to this remaining nums itself, so I need to make a copy of this if I want to do anything to it. So I'll say remaining nums.copy. And now I can pop out these values at index j and I. So new nums.pop, and we're going to remove j first because we know j is further down in the list. Because if we popped I first, that would actually shift all of our indices and our j would be in the wrong place. So we're going to pop j first, and then our new nums will pop I. And now we can recurse. So we've created our value, we've created our new set of nums here, and now we'll do our recursive call. So that just means our value will be increased by the recursive call on what's remaining of our numbers. So this is going to be our new nums. And we do need to decrement our remaining ops because we performed one operation here. We have to take one away from our remaining ops. And now we need to choose, we need to decide if this is the best result so far. So we will need some result. So I'll put the result up here. Let's see, I'll put it right here. So our result will start at 0. Once we go through and we choose some values, we do their GCDs, find their, I guess, resulting value out of this multiplication. Then we'll decide whether or not this gives us the best answer out of all the possible answers. So this is kind of like a subset, and we're choosing the best subset. So in this case, our result will just be the max of our result, or this new value. Now at the very end, outside this for loop, we will return our result. Okay, and that should be it. So we're going through all the possible pairings of values in our remaining numbers. We're going to grab each one of those, find the GCD, calculate this special value out of this operation here. Then we're going to create a new set of numbers. We're removing these x and y that we've popped out of here. We'll remove those numbers, and then we will recurse. We will just perform the same operation again. At the very end, we'll find out whether or not that gives us the best answer, and we'll store the best answer in our result, returning our result when we're done. Now the last part of this is we have to start this whole thing off with at least one initial call to this function. So down here, we'll start this whole thing off by calling, we'll do a return on this max score recurse, and we'll just pass in the original nums. And let's see, what are our remaining ops? Well, it tells us here that we have integers, or we have an array of size 2 times n, and we're supposed to perform n operations. So it's going to be the length of our nums divided by 2. So that's going to be length of nums, and we'll do an integer divided by 2 just in case, although it should be an even number. All right, and that should be it. Let's see if this works. And it works. So let's submit this, but I can guarantee it's not going to pass all the runtime tests, or it won't do it in the right amount of time. This is a very slow algorithm, even though there are only 7 by 7. Even though there are only up to 14 numbers here, this is still a lot of calculation going on and a lot of branching going on with every recursive call. So it's not going to be fast enough. we'll use this test case and we'll see if we can speed up our algorithm here. All right, so what are some things that we can do? I think the biggest thing to me right now is this copy. We are copying this array and popping values out. Maybe there's a better way we can do this copy. The other thing that's standing out is this recursive function. I would really like to either have some dynamic programming to cache the values or use the functools cache method to cache out the values. Now I'll show you what happens if we try to just use the cache method right here. So from functools, actually I'm going to put this above the math just because I like keeping things alphabetical. We'll import cache. And what cache does is cache is a function decorator, so we put it just before a function with @cache. And what this will do is the first time you run a function with a set of inputs, it will run the function, then it will cache out the return value, remembering what the return value is for this set of inputs. If you ever call this function again with the same set of inputs, it will just return the cached values instead of having to run the entire function again. Now, this won't work in the current way we have this set up because cache requires your inputs, these arguments, to be hashable. And these remaining numbers are lists, and lists are not hashable. This is just an int that is hashable, but this list is going to be a problem. So if I try to run this now, it'll probably throw an error. And it does. Runtime error. Unhashable type list. Yeah, so this isn't going to work for us. So this list, not hashable, we can't actually do this caching. But what does work for us is a tuple. Tuples are hashable. Tuples are not mutable, so they are hashable. I guess that's not the only reason why they're hashable, but let's remove this caching for now. We'll come back to that because we're going to be changing this remaining nums into a tuple. So we can keep the rest of this pretty much the same. We can still use this not nums, we can still go through our nums, we can still get the length of nums. All these things are still valid for tuples. But this part, we're going to change. We want to get rid of this copy. So we're not going to do copy and then pop out I and j. We're going to turn this into, well, since it's already a tuple, we're just going to take this tuple and reconstruct it without the I and the j valued, without the index I or j valued numbers. So how do we do that? Well, we use slicing. So we take our remaining nums. Let's just grab this here. So we take our remaining nums and we go up to index I. Now, the way that this slicing works is it goes up to, but does not include index I. So that's going to give us everything except index I, or everything from the beginning to index I, not including index I itself. Then we'll take everything from index I plus 1. So we're skipping over index I, and we'll go to j. All right, and then we will append everything from index j plus 1. So we're skipping over index j, and we'll go all the way to the end of our tuple. So this is taking our input tuple. It's going to grab just the beginning of that input tuple up to index I, skip over index I, grab everything between index I plus 1 to j, but not including j. Then we'll skip over index j and go from index j plus 1 to the end. So this is effectively removing the elements I and j from our tuple. All right. And then we can still just pass it in like we were normally. So not much else changes here. Now the other big thing that does change is because we've converted this into a tuple, our input value here, this is a list. We need to convert this into a tuple, and that's really easy to do. You just say tuple. So you basically construct a tuple from the list. Okay, let's see if this still works. I'm not expecting this to pass all the runtime checks in terms of speed, but this should pass everything in terms of, I guess, just function. All right, time limits exceeded. Not too surprised by that. But now we can go back and use this caching. Because we've converted these lists into tuples, we've made this function a cacheable function. So let's just add our @cache here and try again. And that works. So let's see how we do. Oh, we get a wrong answer. So we're going to use this test case and see what we can do about this one. All right, so we're going through. Let's see what we're missing here. You've seen me make a lot of dumb mistakes on this channel, but this is probably the dumbest. I was typing too fast and I had a typo, and I typed I when I meant to type 1. And I's and 1's look a lot alike. I's and 1's look too similar. J plus 1 to the end, not J plus I to the end. I'm surprised it passed the other tests. All right, now that I fixed that, let's try this again. And we pass. And we do okay. We get 87% for runtime, and let's see, only about 8% for memory. So we don't do great on the memory, but we do all right with the runtime. So there are things that we can do to this basic function. We can go in and clean out some of these variable names, maybe make these a little bit shorter. I don't know if it's worth spending much time on that though. I'll leave that up to you. You can check that out. Try to take this and make it faster. See if you can get a 90% or better. All right? Okay, well, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.